Modern workloads require more from memory than it can deliver. Artificial intelligence, ERP, business intelligence, and other critical technologies require not just fast performance for memory, but also vast amounts to deal with ever larger datasets and increasingly memory-intensive applications. Unfortunately, memory has been historically limited to whatever is built into the underlying hardware, but not anymore. Welcome, I'm Chris Pohl, Content Strategist at CIO Marketing Services, and I'll be your host for today's webcast, titled Accomplishing the Impossible, the Reality of Software-Defined Memory, and brought to you by CIO and Kove. Today, we're going to discuss some of the biggest challenges around memory, as well as a recent breakthrough in software-defined memory that is enhancing performance, ROI, competitiveness, and sustainability. To help us, we're joined by two guests. First up, we have John Overton, CEO of Kove. John, thanks so much for joining us. Would you mind sharing a little bit about yourself?
Sure. Thanks for inviting us along on this. I've been working with Kove as the CEO for a couple of decades now. We've been doing very high-end innovation, and we're now focused on the software-defined memory arena.
Fantastic. Thanks, John. Next up, we have Tom Coughlin, President of Coughlin Associates and President of IEEE. Tom, you're up.
Oh, thank you. Thank you, Chris. Yes, so I'm President of Coughlin Associates. I've been in the digital storage and memory industry for over 40 years, and I and my company, I basically consult and provide market and technology and analyst work, help put on events in digital storage and memory space. Thank you much.
Fantastic. Thank you both for joining us. Tom, why don't I turn the discussion over to you?
Thank you very much. So I have some questions for John here, which we can have some discussion about. And the first one is, what are the big challenges facing technologists with regard to memory today? Go ahead, John.
Well, I think that we're really at a key inflection point. We've known for a long time that compute increases, storage increases, networking. We've never really addressed how the memory surface could become a completely virtualized infrastructure. The current model that you create a server stamp and you just put everything inside of the server is limited, because what happens if you want to do things that can't fit inside the server? And then if you think of it in terms of what happens if it doesn't fit, then what are your options? In the past, that's been traditionally understood through virtualization, but nobody's really cracked the code yet on virtualization with memory, and that's kind of what we're targeting.
Mm-hmm. Yeah, it's been going on with storage, certainly. I mean, NVMe over Fabric, for example. There are some other approaches. I mean, there's various approaches for doing it. I think you guys have one, but there are also, CXL is another approach that's out there. There's a big industry consortium around that. So, what do you think about those different approaches?
Well, from the Kove perspective, we would look at, we're focused on building the best of breed solutions, and anytime any technology is well fitted for or well suited for something, somebody should use it. Mm-hmm. I think almost every technology has a place. CXL, in our view, NVMe, for example, over Fabrics, I think it's a very intriguing extension of storage. Our focus is actually memory. I mean, we're operating in nanoseconds, not milliseconds or microseconds, but nanoseconds. The performance that we provide is the literal local performance plus or minus 1% of the local DRAM. So something like NVMe could be useful, but it's still in the 50 microsecond range. Even if you're putting in, once you put NVMe in there, then you have a stranding issue. So if you use the concept of, I have a server stamp, a cloud-based view of the world, I have a bunch of servers and I fit the workloads inside of the servers, what's the probability or even possibility of being able to use all resources all the time? Well, if you can't virtualize it, you're always going to have stranding of some variety, either DRAM or NVMe or storage or compute. The view that we've got is to change that around. Now, that would be the traditional expansion of storage, which I want to be really careful. I don't think that expanding storage performance is bad. I think it's a part of a solution set, and it's a useful thing. So I don't think that what we do has any bearing on that, but it's very different than what we do. Now, CXL, which is what you also brought up, I think that's a really another intriguing way of thinking about the problem. A couple of issues with CXL. So that's presuming that we're going to have new chipsets, we're going to have new infrastructure, new everything. Our view is we should work with any piece of hardware in the world, and we do. So you can use, we have customers with targets in production for 12 years, and that works still. We hide the latency. That still works like local memory performance from a compute point of view. So the future of the way we would look from a Kove perspective on CXL is it would be a delivery mechanism like other delivery mechanisms. In fact, I would even speculate we're going to see a lot of competition in the world for those kinds of delivery mechanisms, not just CXL. There's HP Cray Slingshot as a way of using it. There's Rocky as another one that people are trying to approach. There's PCIe Express, where you could do a switching fabric off of the PCIe bus. And then there's just straight old RDMA variants that are coming out. In the Kove view of the world, all of those should live heterogeneously and should just work with our software. And then we let the hardware industry fight like the hardware industry knows how to fight and drive costs down.
So you see software, especially your software, being able to deal with resources from many different memory resources in many different places and help to provide the memory where it is needed.
Yeah, I mean, I think that's so we've worked on this problem for almost 15 years, exclusively this problem, maybe 10 active years. We went and back in the mid 2000s, we looked at the physics of various memory technologies. We've really gone all in for quite a while, and our view is that if you look at the history of computing, I think there are some big trends that repeat over and over. You move from a highly generalized, kind of big iron infrastructure to something that's highly distributed, and it swings back and forth every couple of decades. You move from something that's specialized and high-end to something that's commodified and distributed widely, and that you move to commodification. In every one of these cases, it leads to virtualization. You had CPUs, then you had cores that were virtualizing computational infrastructure, then you had virtual machines, now you have containers. Same thing happened in storage, same thing happened in networking. No one's really kind of figured it out, and people have worked on it for a long, long time, how to do it with DRAM. That's kind of what we focus on and are delivering, fortunately.
Maybe that brings into the question is, what are the pros and cons of various alternative memories available today? You mentioned DRAM, but let's talk about those memories, different types, and maybe even things like, especially in these AI applications, like high bandwidth memory, for example. There's sort of a new hierarchy of memory that's being created. It might even include some emerging non-volatile memories as well eventually. Can you talk a bit about that?
Yeah, 100. 100%. I mean, I think we're really at an inflection point where lots of new approaches, are being brought to bear. One might argue that the value of increased computation is diminishing against, on one axis against the increase in memory and storage. I think the storage wonks that really understood storage saw this well over 10 years ago, and they started focusing on storage as the most cost-efficient way to improve the functionality that workloads could provide. I think we've hit the limit of where that really goes, and now we're focusing on memory. Inside of the memory hierarchy, high bandwidth memories, it's very exciting, right? I mean, there's our view as a software layer is those are all hardware selections. We have spent, I think we work with every Linux kernel in existence, and I think we work with every piece of hardware that's supported by the Linux kernel. The reason that we spent so much time on that is we'd like to give customers the ability to build the best applications and performance possible. So let's look at high bandwidth memory, for example. There are going to be application suites where that is magical, where it's just how much bandwidth can I give you?
Like artificial intelligence. Yeah.
Exactly. Right.
Yep.
And, our view is we would be wanting to saturate to the degree that the servers can receive IO. And that's what we do. So we would be limited to whatever bus infrastructure you would put on a motherboard. Now that bus infrastructure is likely to be less performant than the really fast memory because you can't keep up with that. but we can saturate that and then allow the customer to build the best way to use the high bandwidth memory for AI, for example. But I think we're even just at the beginning of that. Bus technology is going at huge speeds. High bandwidth memory is going to be ever increasingly integrated into the solution stack, into the chipset, to avoid some of the software overhead. In contrast to that, our approach is you can get signals and understand what's going on at the application layer through software that you don't get through hardware. Hardware, it's just statistics. We actually see, we can understand how locality of reference is being manipulated, what the instruction set is doing, what kinds of patterns are going to be reproduced or used that need to flow into the compute infrastructure. That's something that we've been studying for almost a decade, and we have very sophisticated tooling to be able to allow that, which is a part of how we hide the latency.
Well, one of the things people are talking about is distributed computing, new ways of doing that, even across data centers. And another one is, domain-specific processors or accelerators, which could be near the memory itself. So how does software-defined memory work, say, in these distributed computer architectures, or, in an architecture that includes various accelerators to do local processing of data? Maybe it makes it more efficient. Maybe it speeds things up.
Yeah. I mean, it doesn't surprise me. These are outstanding questions, right? So, it makes it fun to talk about it. So on the distributed side, our view of the world is whatever the funnel is that leads to where the compute is done. Our job is to provide the fastest, what we call deterministic, the greatest determinacy into that infrastructure. So if you wanted to have a highly distributed, compute infrastructure across distance, for example, we actually are talking with a government about something across a country along these lines, where you could imagine having distribution centers of memory fabrics, and you can have optical, bandwidth across distance, and we could use the same structures that we're doing internally inside of computers with regional distribution centers for memory. It's mind-numbing. Nobody has been thinking about something like this because everybody's
the latency differences, how you handle that,
Exactly. And the issue there comes down to what you can do in software. That's very hard. And one of the challenges, I think, why we got here a little bit faster than a lot of folks is the inherited wisdom is everything moves into the chipset. I think Intel convinced us of that, decades and decades ago, and we consume that as inherited wisdom. And I think there's a lot of truth there. So, I want to live in a world where I don't have to go to one far extreme of nonsense to make the point of another side, right? That we can keep two ideas in our head at the same time, right? I think there's lots of value of moving into the chipset. I don't think that goes away. But I also think, especially when you go into AI, where you get lots of patterning and you get lots of repetition of high volumes of consistent but slightly different information that is run as in parallel as quickly as you can.
Some predictability.
You got it. You all of a sudden can see the patterns and you can anticipate the patterns at a software layer that you would never imagine to even attempt to do in the hardware. That's what we do. So all of a sudden, things like these distribution channels that you can imagine, which would have been unimaginable, not even imaginable 10 years ago. Yeah, there's ways that you can take a swing at that. Now, that answers the kind of highly distributive approach. If you go to the other way, which of course is the more move it closer into the chipset, where I build special
or within a local network or something,
or within a local network, the same patterns apply at the software layer. If I can understand at a software instruction set what's highly probabilistically going to be privileged or prioritized, then I can work with those infrastructures very naturally. And then the game is, can I feed them at a rate that is near or equal to their rate of churning inside of that infrastructure? If I can create the right timings, we've shown systematically with CPUs that we can. We've had people, for instance, back in 2012 or 13, I don't remember the years, but a while back with Haswell, whenever Haswell was. So whatever that year is that Haswell, this is that time. But we had a trader in financial services hitting, and I'm using numbers, and this is over a decade ago. So I'm sure there's a fact checker and somebody could get my numbers wrong. Okay. I'm remembering on the top of my head, but it was something along the lines of a hardware theoretical of 55 gigabytes of sustained computation in the processors. And in that application, we were hitting 51 gigabytes, or we were within 5%, 6% of hardware theoretical of the CPUs by doing this. Now that was specialized infrastructure where the trader knew 100% the whole worldview. There was no automation, but that was 12 years ago, 10 years ago that you could do that. We've spent a lot of time figuring out what those patternings look like. So AI is like manna from heaven. We can do things that you would never imagine. So for example, we have a customer, and they did apples to apples testing using a very well-known virtualization manufacturer that I don't try to use names and these kinds of things, but it would be somebody that everybody knew who they were. And they did apples to apples comparison of that versus OpenShift, where all they did was hit buttons to install us. We were 60 times faster, 60 multiples faster with no code changes on the AI modeling because of this. You can do some really interesting things.
So with well, you're kind of using AI to work with AI.
We are.
You're looking for patterns, right?
We are.
Yeah.
I mean, why not, right?
Makes some sense. So what do you think then, and you've kind of gone into some of these, but maybe you could summarize and maybe expand a little upon the transformative capabilities of applying software-defined to memory?
Yeah, I mean, so it's you've given me an abstract space to talk about, which is dangerous because now I can go on forever. I can almost go on forever as it was. But
where will this take us? What will we be transforming in the future with software defined?
I think software defined memory is one of the, if not the most, it's one of the top couple of the most significant innovations for AI. So we have a customer that does some very high-end AI in genomics. And to push one more gene sequence of where they are, memory expands quadratically. Okay? One gene sequence.
Yep.
The power used for a machine that they have is the equivalent of between 30 and 40,000 U.S. homes. Okay? Now, imagine that you have to expand the memory quadratically for the next meaningful increment. So how many cities of power do you want to build? Okay. How does that go?
Yeah.
Well, what if you could take the aggregate of the memory that you have and you could apply it mathematically, cache coherently, dynamically to exactly those processes needing more memory across that machine, across those machines? That changes the way you can do it. LLMs, the same problem. The problem is not, can you get enough CPUs? We know how to do that. The problem is, how do you get enough IO to feed them? Storage can't do that because it's too slow. Even the fastest and best storage. It does lots of really useful things. You got to have memory. And if you're going to do memory, it's too expensive. It's 65 to 85% the cost of a server for big memory servers. So what are you going to do? Buy cities of memory? Well, what if you can just use the memory you have more intelligibly and intelligently? That's the game. That's software-defined memory.
You know, I just, this last month, I had a chance to go to CERN in Switzerland.
Yeah.
And they were telling me about their data growth and, scientific experiments, astronomical data, things like that. It's like the amount of data that's growing is just enormous. And a lot of times, and you mentioned about, doing things over the network, they're collaborating with people all over the world. So they've got to have replication of data in various places. The throughput of collecting that data is just enormous. You think software-defined memory can help on that?
Well, so this is a little bit like when you're when one is finishing one's dissertation. Everything you see is what you've been working on for the last 5 years.
Yes. Everything looks like
and it's like, of course, there's nothing that we can't do, right? I mean, it's just easy, right?
You got to hammer everything looks like a nail, right?
Exactly. I mean, I'm putting a little disclaimer in here because,
Sure.
I mean, there's certain things that software-defined memory is really going to be game-changing for and certain that aren't. We're not going to change the speed of light, the width of the cables, the distance of going up and down satellites, to move, multi-hundred terabytes across the world, right?
Right.
There's things that it's not going to do. Having said that, if one could imagine a scenario where you wanted to do extraordinarily large computation, and you could understand the patterning, you wouldn't have to move the data, right? You would move the compute.
Okay? Yes.
And you would invert that, and you would go to where the rich data sets were, and those could exist in ginormous volumes of memory. And you would move the compute in some rational fashion so that you're segmenting the computation across distance according to workload, not according to payload.
So this is software-defined computing.
You've got it. And
yeah.
that's what I think is one of the next things that happens is once you know that you have indiscriminately performant, arbitrarily scalable memory surfacing, then what you need to do is to be able to do these kinds of dynamic configurations. And the first thing will happen is in the data set and, high-end, scientific computation. And then the next thing will happen is it'll go into the data center or the cloud. And then after that, you'll start having people thinking about these massive new ways of collaboration, international collaboration. I think it's all coming. And I think software-defined memory is in the middle of that. You can't get there until you've solved that. And then new problems. Yeah.
It kind of seems like to me like, you're almost talking about like creating the internet, right? Potentially, if you're going to be working with computers all over the world, you've got an unreliable compute fabric. And can you allocate resource? It's going to have timescales are different, than communication, but allocate resources based upon, looking at the network, looking at the demand, all kinds of stuff that software would be great at trying to make happen.
So we had a huge inflection point, actually, about, it would have been 2007 or 2008. We were getting ready we had designed a board on the assumption that the only way you could get memory to work effectively is to find a clever way to put more boards inside of servers because of the speed of light, distance of cable problem.
Right.
And I had some folks on the team really upset with me because they were like, we're going to destroy our future, right? Because all that does is it's going to be a card, it's going to be a board, and we're going to sell the company. And, we all signed up because we want to build something over decades. And there's a conference room down the way, and we kind of got in a room. And I said, look, you guys come up with the ideas that are better than what I'm proposing, and we'll change. And we spent a weekend, and then we got rid of the board, which was my idea, by the way. So it was not an easy one to give up. But the view was, if you don't solve this with software, then we will limit the scaling of this at some point. And this is back in 2008 that we were thinking like this. I mean, this is the fortune of being able to be a small, agile, company across time, is that people were thinking, on the team, developers, the only way this works over time is you have to look at memory as an abstract service, the way you look at storage or the way you look at compute. And the only way to do that is you've got to solve the latency and the speed of light, distance of cable problem. You can't give up cache coherency. You can't give up commodification. You can't go into specialized because all of those are going to have limited lifespan. You've got to go to the generic. And we had the patience to do it. And the payoffs have been, profound for us.
So, do you think the time is right? And what do you think it will take for software-defined memory in particular, working with all these other software-defined capabilities to become widely accepted and used universal or used in many different applications? Then we'll talk about what those applications are.
Yeah, sure. So I think I have a couple of general comments before I kind of drill in. I mean, one is whatever that old adage is if you don't learn from history, you're subject to it. We in the history of computing, things always move to commodification. There's no element that hasn't. Okay, ever. Right. The question is when. Things always move to software virtualization. Everything, and there's never any instance where that's not been the case. The question is the timeline and the architecture. Typically, you get a dominant vendor that specializes in some kind of hardware innovation, and then they sell that effectively. And there are lots of illustrations of that in the chip manufacturing. Mm-hmm. And then it moves, we're now getting into standard definitions of servers that are consortiums where people will be able to abstract, server definitions, right? No longer a server vendor.
Or even, basic chiplet-based systems where they even 100%. Components are bespoke,
Yep. I mean, that's what happens, right? Yep. So, the view of kind of, if you don't solve that in software, you lose the genericism to allow the marketplace to compete, right? You have to bet on people will build better and better hardware, more efficient machinery. You have to bet on that, and that has to be your friend. Not something that you're outrunning, but something that you want to run into you. And that's a key assumption that Kove made, really a long time ago. So we've worked on a particular software stack for 15 consecutive years, and we have not had in the history of the company ever any innovation that didn't just work. I mean, we built it. We worked. The definition of how we've done it, we work with the AMD 64 specification. So our ability to address memory is related to whatever the specification is. If that changes, we change. Our performance limit is the limit of whatever the computation infrastructure is inside the server. So whoever solves that, however they solve that, we solve the problem that feeds into the server. These are architectural design issues that we spent almost 2 years in a white room development. Might have been closer to, it was between 1 and 2. I think 2 is a little bit, is more than 1, less than 2, where we wanted to make sure that we worked with all open interfaces into the infrastructure of the compute, simply because we didn't want to have to worry, somebody came out with something that we didn't think about. Right? That used to be the way companies were built, that you were building, the best that you could build. So I think that in terms of the software, the generic, dimension of where software-defined memory goes and how it's built, it has got to be at the software layer, and it's got to be generic, and it's got to work indiscriminately with any kind of hardware. And that's part one of the universe. And then the second part about what makes that adaptable or usable? If it works with anything, you let the market decide that, right? That's not our problem to solve, right? I mean, if there's no hardware limits, this is one of the objections I'd make to some of the consortiums. For example, we're a fan of CXL. If CXL wins, we will be we will power that to its limits, right? No problem.
We'll be able to work with CXL.
Yeah, and that's going to come out. We're shipping products where you can have data center memory, for over 9 or 10 years. That's not even on the roadmap for CXL. And then you got to buy new hardware. Right now, you can buy any hardware, and you can hit 3 buttons, install our software in 40 minutes, and you're up and running. Okay. So in terms of the, what's going to be involved in, going back to the core of those are the abstract principles behind the core of the question of, what's necessary for this to become used. I think first of all, we have to change our mindset. I mean, we think, it's all about the server stamp. What if it isn't? We don't think that way about storage, right? We did. How much storage can I put in my server? When was the last time anybody thought that way? Right?
Don't anymore, because they got used to allocating it as needed.
Right. Well, why can't we do that for memory? Well, because of our mindset. Because people say, I can't tell you how many times when we go in, we talk to folks, the first question is, what's latency? You can't solve physics. It's the speed of light, distance of cable. I mean, and I understand why people say that, because we spent 10 years on that problem. Right? It's a real problem, right? But it is solvable. And if it is solvable, then the adoption problem has nothing to do with the technology. I mean, we're used right now in the backbone of the financial services, arena for SWIFT. They do 93% of all money transfers globally.
Yep.
Right?
Yep.
I mean, it's real. You just got to open your mind and say, well, what if I actually could think about memory the way I think about storage virtualization or networking virtualization or computational infrastructure? If I could, well, then I would build different systems. I'd build different data centers. I'd build different servers. I would, no different than any other virtualization play. Does that kind of get to the core of the spirit of your question?
I think so, yeah. But the next thing is, what are some particular use cases where you think we'll see near-term benefits for software-defined memory?
I've got a bunch that are not even near term, but immediate.
Yeah. Okay.
We have, we've done a bunch of measurements with Red Hat and Supermicro, and we've demonstrated that you can use software-defined memory to reduce power signature at the data center level between 12% and 54%. No code changes.
Wow.
No code changes.
Because
all you do is install it.
Yeah. That kind of ties into sustainability, ESG metrics, especially data centers.
Carbon footprint. Okay, no problem. I mean, but think about it. If I don't have to run everything hot because they're stranding, and I only run what I need when and where I need it, I can play with things I never thought to play with before, such as power. Okay, that'd be one.
That's interesting.
Genomics, gene sequencing LLMs. How many cities of power do you want to buy per machine? Okay, you can decide, government, what you want to do. Okay, I mean, or why don't we just get smarter with what we do and solve the problem, right? I mean, and the people, and we are dealing with folks like this, the people that are, the old-fashioned technical people that are solving real problems get value immediately. I mean, within months. Okay, next, time to solution for AI. So let's talk about the day in the life of, I'm going to train my model 1,000 times. So, maybe that's a high, maybe it's low, depending on who it is. I'm going to get, some big servers or server farms. I'm going to fill them with GPUs. I'm going to have all my data scientists together. We're going to figure out how it is that I'm copying data from the motherboard into the GPUs, and then how I'm managing it across all of the servers. And I'm going to run my job. I got to run it in memory because I'm going to train it 1,000 times, right? So if I hit NVMe one time, the fastest NVMe is 125 times slower than regular DRAM. So let's say that I have 100 servers and one of my servers hits NVMe. A 4-hour job times 125 is 19 days. So I'm just going to stop all AI development for 19 days of the other people I'm paying $500,000. Of course I'm not. I'm going to turn off my NVMe. I'm not going to use that as a swap cache extension because it's too expensive of a risk, not money, but of a risk, time risk, machine risk, human risk, allocation risk. I'm going to turn it off. I'm going to crash my system because I want to be off that system if I'm not being productive with it. So now what I do is I'm not stupid. So I realize, well, if I'm going to do this computation across 100 servers, I've got to be very careful that none of those servers is going to have a computational moment in my 4-hour cycle that I'm targeting that's going to go above the local memory. Right? That's dangerous because if it does, I'd swap my crash it. Now I have to wait my turn for the next. Well, let's give you another view of the world. If I have software-defined memory, if I don't have it, I'm going to target 25, 30% of the local memory on the assumption that one of my processes out of the 10,000 or 100,000 processes spikes 2 or 3x.
Right. You over provision. Yep.
Right. This is a classic old school storage provisioning once upon a time ago when it first came out. That's what you do. So now go to my bosses and I say, I want you to buy me the biggest, baddest memory servers because I'm going to use 25% of them. Oh, that's 65 to 85% of the cost.
Yeah, exactly.
Okay? Well, what if I could use any server that's in the data center as a memory target, and I can hit you the same performance plus or minus a couple of percentage points as the local memory? Then that's
better than NVMe. Yeah.
I mean, it's within a percentage of local memory. Exactly. Okay. Now let's go back to that same instance. I now, instead of using 25% memory, I use 75% memory, and I allow any server to be able to draw from a pool of memory to go 3 times, 4 times larger than the physical server. I've now tripled or quadrupled or quintupled the accuracy of the model because I'm able to compute more in the same time frame. That's right now you can do that. Like right now. Okay, now that's one. Now let's imagine that not only that speaks to improving the model accuracy.
Yeah.
Okay.
Well, and also the runtime.
Well, there's the next one, right? So I've got to train that 1,000 times, right? What if I have fewer failure rates? I have higher utilization of the hardware that I'm spending. I have better energy utilization because I can target what goes on where across those computations. I can now improve the time life cycle of the data scientists. That's my most expensive labor right now. Instead of having them spend all the time segmenting the data and planning and plotting on how to fit the workload into the hardware.
Right.
I invert it. The hardware fits the workload.
Mm-hmm.
You can't do that unless you have software-defined memory. It's completely game-changing.
Mm-hmm.
You can do that literally right now, right? That's, not, okay, that's another use case. I'll give you another one. The only way smart cities are going to happen? Software-defined memory.
Because you're going to have to use resources depending on where things are happening.
Yeah. So I'm going to I've got a self-driving car. Next time you're driving a car, close your eyes and count to 3 seconds. Okay. Imagine that. Okay. You know what? Just blink your eye, because that's the speed of light up and down a satellite, 200 milliseconds. That's about an eye blink. Okay. So every 3 seconds, blink your eye as you're driving. How safe do you feel? Okay. Now we're going to give that over to AI agents to drive the cars. That's what it means to go up and down the cloud.
Yep.
It will not work.
And that was where people get into local intelligence. And even Apple, they're talking about doing that with their devices, for example.
It has to be done that way. Okay, so now I'm an organization like Verizon, a large telco. That's the natural infrastructure is going to be telcos for these kinds of things, because they have the best, wired and wireless networks, around the country that can manage locality, as opposed to going up and down cloud satellites, right? So I'm going to use those folks for my delivery mechanism. The next thing they're going to start thinking about is, well, what kind of compute infrastructure do we want to provide our customers? So here's a great idea. Why don't they buy the most expensive hardware that they can buy and populate it in server stamps all over the country and just charge the customer more money, right? That's a great idea. Buy terabyte servers that you use, only randomly when there's a congestion in one part of the city or when there's an emergency, right? What if instead you bought smaller, less expensive servers that had memory that could move around, that would allow you to build specialized computational resources? You could have specialized chips, just like you had alluded to earlier, Tom. In the servers. In the city, you might have an instance of 30, 50 pops, around the city, and you might have those are all within 3 millisecond cost range. No, not 200 millisecond. 3 of the network.
Especially at like a 5G or 6G infrastructure, because you have to have so many antenna locations.
You got it. All of a sudden, the latency is all within that city. The problem isn't going to be the latency going up and down the satellite versus in the city. The problem is, what's the computational resource? In Kove's view, we're going to expect that there's going to be some pods in that city that are going to have specialized computation for certain kinds of things. Some pods that are going to have other, and they're going to move the workload to the hardware, right? And then the hardware is going to shapeshift to fit the need of the workload. We can do that right now. We have folks that are doing stuff like that right now. That's software-defined memory.
One other thing too is that if you're moving the memory around, and it's another thing you do is what's the capability of the memory? Where is it at in this life cycle? Or there are issues, error corrections, things like that. Maybe you can anticipate some of those things as well in terms of where it is you allocate where it is you do calculation at.
I think, again, you can swing the pendulum from big to small. Let's imagine that you're in a data center context or in a rack context. If you have distributable memory, what's your time to recovery? It's a new allocation request, right? So if you have a server and you're bound to the server and you lose a DIMM or a rank on a DIMM, you got to call your Dell rep or whoever your rep is. They come in 4 hours, they rush, they turn the machine off, they stick a new DIMM in there. Okay, if you're using software-defined memory, you fail, you get a seg fault, you request a new piece of memory, and you go to a different machine.
Right.
It happens in less than 200 milliseconds, 4 hours or 200 milliseconds.
So you can have soft failures, recoverable failures, things like that. Yeah.
You can still use all the same hardware stuff if you want a rank spare, you want a memory mirror, you want to do all the stuff that you can do in the hardware. You can still do that. But there's another way to do it, which has very different cost efficiencies and it still provides you the same performance and way more flexibility and resiliency.
So maybe that gets into my last question here, which is software-defined memories adoption, how that changes things. We talked a lot about this from the technology side. How does it change things for the business side, for those that are actually building data centers, those with projects they're trying to run, et cetera?
Well, so I've been trying to avoid talking about Kove in a salacious business perspective, but this is hard not to, right? So imagine the scenario where you could say, I'm going to reduce the power signature of every data center I have worldwide 20% by installing software. Okay? No code changes. Just do it.
Wow.
Okay? You could do that right now if you were so enlightened. Okay? Imagine a scenario where I say, I want to be able to provide, 300 terabyte servers for a customer for 11 minutes or 2 hours or 19. How am I going to buy that server? I go buy a supercomputer. What if that was just a provisioning request on unused hardware in your data center?
Right. So you could turn this into another, essentially, computing as a service sort of capability. Computing memory as a service. And you essentially rent out resources wherever they're at. So that could be part of the part of what you're doing. So sort of a new type of cloud, a new distributed clouds.
100%. And you could do it with just software, so you don't care about the hardware.
Right.
I mean, it's a different. Again, the biggest problem with software-defined memory is we have such a legacy inheritance that because of the speed of light distance of cable problem, that you can't do it. Therefore, you've got to improve the server stamp. Right? It's the same problem initially. If you go back far enough, I've read up on you. You have a very insignificant storage background. And that's a wild, sarcastic comment for the people who are watching this. Okay, max out sarcasm. So, but you go back enough in time, and people would say, well, what are we going to do about this? Storage. The payload's too expensive to push across wires. We got to keep it in the box, right? Until we figured out how not to. And then all of a sudden, you had a new industry. Same thing if you want to go into, something like a virtual machine, approach, right? Oh my God, what's the overhead? I have a virtualized OS. No one even talks about that. It's still there. It's a 10% overhead. Okay. Memory, it's a 1 or 2% overhead, not 10%. It's better than virtual machines. But people just look at it because, oh my God, look at what I can do. I can do way more than I ever could have done. The memory is the only remaining component of virtualization that hasn't been done. That is the place. And it's the most expensive.
Yes.
And it's now, right?
So essentially, we're going to see, it sounds like we could see dramatic changes in the economics of running data centers, the economics of doing things at the edge. Basically, wherever it is you use memory, you now have new resources available for you to do whatever it is you're trying to do.
Well, let me again swing big, swing small. Let's now imagine this scenario that instead of saying, okay, one of the initial things that ideas that people latch onto with virtualized memory is, well, that means I can have bigger servers. Well, that sounds niche. Well, yeah, I mean, it can't be niche. The other is you can have much smaller servers. Because
maybe both.
As an assignable resource. What if my server stamp changed its economics completely and I had the best of breed compute, whatever that is, with a nominal amount of memory, because memory is for free. I have reduced the size, the power, the signature, the cost basis of the stamp. And then I assign it memory whenever it needs. And it's 1 or 2% difference in performance. I've completely changed the CapEx and OpEx support infrastructure for that. Okay, now one last one on this. Now imagine privacy. I mentioned we do some stuff. Well, here's a great idea. I'm going to bet my privacy because I think, Google, Microsoft, Amazon have the best, smartest people in the world, and they're going to protect the privacy of the world's economy. Great idea, right? What if I could build systems that are more efficient than built on stamps? Because I'm now building configurations according to need. And I can build them locally less expensively than I can in the cloud or on the edge. I mean, this is the beginning of swinging back from cloud back the other direction. And as I started off my first, comment, if anything, those who don't learn from history repeat it, right? Things go all the way one side, all the way other, and then just keep, and they're multi-decade swings. Software-defined memory is the first really component. There's going to be new software that will be written for the people who are capable of still thinking like that and writing the best of breed applications. They're going to start using it to swing it this way. It is incredibly exciting.
And it'll change the way we design hardware as well, right?
Everything.
Yep.
It's the most exciting time. It's been a long time since I think there has been this kind of an innovation that is foundational across the whole surface of the way you think about, computation. I mean, there have been many of them. This is one in a history of many others, right? Storage, computational, Beowulf clusters, you can go through the list, right? But this is the next one. And, and I'm not going to say it's the only one, but the way we've approached it is we presume, again, it goes back to this conversation where I had people who were going to throw things at me in our conference room, almost 15 years ago. If you solve this in hardware, you're doomed, right? Let the market solve the hardware game, right? Go in and provide software that lets you work with any piece of hardware, period. And then you get these economies of scale across the marketplace.
Yep. Well, thank you, John. I really appreciate the chance to have this conversation with you today.
Tom, it's a blast talking with you. It's really nice. It's a pleasure. Really.
Likewise.
Yeah, thanks so much, Tom. Those are some great questions. And John, appreciate your passion, appreciate your insight. Thank you both so much for joining us. Unfortunately, that is all the time we have for today. I wanted to take one last opportunity to thank both of our guests. We had John Overton, CEO of Kove, and Tom Coughlin, President of Coughlin Associates and President of IEEE. And thanks to you, of course, our audience for joining us. Today, we explored some of the biggest challenges in regard to memory, as well as Kove's breakthrough in software-defined memory that is enhancing performance, ROI, competitiveness, and sustainability. For additional information on software-defined memory and Kove SDM, please take a look at the resources section on your screen, where you'll find a lot of great assets, among one of which is a white paper titled Maximizing Performance Beyond Hardware Limitations. And if you're interested in getting started with Kove SDM, you can visit kove.com to get in touch with a team member and learn more. For CIO and Kove, I'm Chris Pohl.